Okay, welcome to part C. The Lawnmower Serenade has started up again, but I think it's far enough away now that it won't be too much of a problem. So let's go on to derived units now. Derived units are, derived units are formed from combinations of other units. And some examples of derived units would be the units that we use for measurements like, for instance, volume, and also area and density. And so we'll have a look at those. Another derived unit would be speed. Miles per hour is the number of miles traveled divided by the number of hours that it takes to travel that distance. And that would be considered a derived unit because it's a combination of miles and hours. In the SI subsystem of the metric system that we use in chemistry and physics, the standard unit for distance is meters instead of miles, and the standard unit for time would be seconds rather than hours. So meters per second would be the standard unit for speed or velocity in chemistry and physics. So as for the types of derived units, as I mentioned a moment ago, there's area. Area is usually thought of as length times width for regularly shaped areas anyway. And a width is a type of length, so it would be measured in the same units. So an area is usually represented as length units squared, or length units to the second power. In the SI system, the standard unit for area would be square meters. But also, any length unit squared would also be an area for, also be a unit for area. And there is, as I mentioned, a special unit for area, which does not take the form of length units squared, and not explicitly anyway, and that would be acres. Volume is also a type of measurement that normally uses derived units. For regularly shaped objects, volume is usually considered to be length times width times height, and width and height are both types of length, and so they would all be measured in the same units as length. And so what we end up with for volume is length units to the third power, or length units cubed. So any length unit to the third power would be a unit of volume. The SI official unit for volume would be cubic meters. Although, like I said, any length unit cubed would be considered a unit of volume. So it could be cubic centimeters or cubic feet or whatever. There are special units for volume also. In the metric system, we have liters. Liter is actually related to a length unit to the third power. It just doesn't say that explicitly. Because it turns out that 1 liter is the same as 1 cubic decimeter. If you refer back to the prefixes, you'll see that deci means 1/10. So 1/10 of a meter would also be 10 centimeters. It's about like this. Whoops, about like this. And I know you're watching this on a screen, so it might be bigger or smaller, but this is a standard 8.5 by 11 inch piece of paper. And so it takes, 1 decimeter would take up maybe about this much of a standard piece of paper. And if you think of, say, a box that's about this much on each side, that would be about 1 liter if you think of comparing that to, say, a 1 liter bottle of Coke. That would be about the same size. So 1 liter is actually 1 cubic decimeter. This relationship here can be very useful to remember when it comes time to do unit conversions. Okay. There's also the milliliter, which is commonly used in the metric system. Turns out that the metric system, they were really thinking when they set up the metric system. They set it up so that a liter is the same as a cubic decimeter, and they also set it up so that a milliliter is the same as 1 cubic centimeter. This can also be useful to remember when doing unit conversions. And of course, in the the English system, we have gallons and their derivatives like fluid ounces and things like that. All right. And so next we come to density. Density is the amount of matter in an object or sample relative to its size. And when I say size, I mean its volume, how much space it takes up. So how much matter you've managed to cram into the space relative to the space itself. So density is equal to mass over volume. So the mass of a sample or an object divided by that same sample or object's volume. And by the way, there is a symbol for density, which is the Greek letter rho. It's actually their equivalent of an R, but it looks more like kind of a fancy P, which is often used for density, although it's more in physics than in chemistry. But just in case you see that, that also means density. When you have a 3-term equation like this, it can actually be instructive to place the 3 terms in a triangle that would be set up like this. And where you place the 3 variables, density, mass, and volume, depend on how the equation is set up. In this case, we have density is equal to mass over volume. That means that mass is on top and volume is on the bottom. So mass has to go in the top space and volume has to go in the bottom space, one of the bottom spaces, and then density goes in the other one. And the nice thing about this is if you set this triangle up correctly, you can always write, basically it helps you rearrange the equation. Because very often you'll know the density, it'll be the mass or the volume that you're looking for. So we set up the equation knowing that density is mass over volume. But say, what if you want mass? That would be density times volume. What if you want the volume? It's mass divided by density. And so now you've got the relationship between all 3 of those terms very easily and very reliably without having to go through all the rigmarole of converting or rearranging the equation. Density, before we get into doing any actual calculations with things, let's go back to what density actually is. And it turns out that density is a characteristic property of any pure substance. Now, for various substances, it may be necessary to make sure that you're measuring at a certain temperature and pressure because temperature and pressure can have an effect on densities, especially for liquids and gases, but also a little bit for solids. But as long as you're measuring at the same or near enough temperature and pressure, you can actually basically look up the density for any pure substance in a reference book. You don't even actually have to find it yourself. And that's why I say that very often we'll be using this equation to find mass or volume rather than density, because densities are already known for just about everything out there. They've been tested and they've been written down and cataloged and put in reference books. So we don't usually even have to find the density. But if you do find the density of an object, that can actually help you identify it. Because if you can find out what the density of that object is, you can match it up to the known densities in reference books, and that'll tell you what the object most likely is. You can probably think of sort of an example of doing that in everyday life. If I gave you a piece of gray metal and asked you, is that piece of metal aluminum or lead? You would probably be able to tell me without even doing any calculations or measurements on it, because we all know that lead is really heavy relative to its size, which means it has a high density, and aluminum is really light for its size. In other words, aluminum has a very low density. And just by holding the piece of metal in your hand, it's usually pretty easy to tell which one it is if the choices are lead versus aluminum. And so that is just a case of measuring, at least in a ballpark estimation sort of way, measuring the density of the object and comparing it to reference values, again, at least sort of approximate reference values that you have in your head. Lead is really dense, aluminum isn't. And you can do more sophisticated versions of that in the laboratory, and you can actually identify things that are much more similar to each other, like maybe zinc versus tin or something like that. Okay. Turns out that density is also a characteristic property of mixtures, but in each case you would have to specify the composition of the mixture. So if you have two mixtures that have the same stuff in them in the same proportions, they should have the same density. What's another interesting thing about density is that it's what's known as an intensive property. An intensive property is one that doesn't depend on how much of the substance you have. So that's another reason that you can find the density of a substance and compare it to the known values to decide what it is, because it doesn't really matter how much of it you have. The interesting thing is that mass and volume are both what are known as extensive properties, which means they do depend on amount. I mean, obviously, the mass depends on how much of the substance you have. The more you have, the more the mass is. And same for volume. The more you have, the more volume you have. But when you take two intensive properties divided by each other, you get, or sorry, you take two extensive properties divided by each other, you get an intensive property, one that doesn't depend on how much you've got. And so that's one of the advantages of density. It can work for any amount of a substance. Okay. Okay, and what I'm getting at here is that when you have objects in together, lower density objects tend to rise above higher density objects or substances. at least for liquids and gases. It can happen in solids too, but it tends to happen very gradually. So when you think of, say, oil and water, oil, whether it's motor oil from a car or vegetable oil from the kitchen, tends to have a relatively low density compared to water. And so when you mix oil and water, you can try to mix them up, but they won't stay together because they're two different types of molecules. And when they separate, the oil will go to the top because it's less dense. And the water will be on the bottom because it's more dense. Same with helium balloons. The reason that helium balloons rise in the air is because the helium is less dense than the air. And so it tends to rise up, and it's the difference in densities is enough that it's actually able to lift the mass of the balloon with it, and it goes up and up into the atmosphere until the air is so thin that the density of the air and the helium are equal, and then the balloon basically stays there. So this happens depending, this happens as long as that's assuming that the substances don't react with each other or dissolve in each other. I mentioned the example of oil and water. When you put oil in water, the oil rises to the top. Alcohol is also less dense than water, but if you put alcohol in water, it doesn't rise to the top, it mixes in with the water. So the alcohol will dissolve in the water. So that would be an exception. So let's see, the units for density. Well, it's mass over volume, so density units would be mass units over volume units. And actually, technically, any mass unit over any volume unit could be considered a density. But in the SI system, we have certain units that are standard for those two quantities. The standard unit for mass would be kilogram, and the standard unit for volume would be cubic meters. So those kilograms per cubic meter would be the standard unit for density in the SI system. Okay. In practice, kilograms per cubic meter, not really a very convenient unit to use. Kilograms are awfully big as a unit of mass. A lot of the stuff you're dealing with in the laboratory is present in fairly small quantities. So why would you measure the mass in a huge unit like kilograms? You're probably going to measure the mass in grams. Cubic meters is also a pretty big unit for volume. A cubic meter is actually a little bit bigger than a cubic yard, which is pretty big. So you'd probably use a smaller unit for the volume as well. And that's what we normally do. It's just that we then have to be able to convert those units to kilograms per cubic meter if we're going to use that density in certain equations. The more common units for density in the metric system would be, for solids, grams per cubic centimeter. Because we're assuming that, well, actually in this case, we're assuming that the solid is a regularly shaped solid. And so we're considering measuring the volume as being a measurement of length and width and height. And so that would give you length units to the third power. And the most convenient length units to use for smaller objects would be centimeters. For liquids, the most common unit would be grams per milliliter. Again, grams because it's a reasonable size unit for most laboratory size samples. And also milliliters because most liquids are are measured in glassware in the laboratory, which is marked off in milliliters. But notice one thing about these two units. I said a moment ago that a cubic centimeter is actually the same thing as a milliliter. So in practice, those units are actually the same thing. Grams per cubic centimeter and grams per milliliter are actually the same unit. And if you measure the density of something in one unit or the other, either way, you'll get the same number. In fact, many times, if you have an irregularly shaped object, which you can't measure easily with a ruler, we will often measure the volume of it by displacement of water. So you put some water in a graduated cylinder, and then you drop the solid object in, and you read the new level of the water. Basically, the object you drop in the graduated cylinder will push the level of the water up, and the change in the level of water should be the same as the volume of the solid. But if you're reading the volume as the change in the volume of water off a graduated cylinder, then you actually are technically getting the volume in milliliters, not cubic centimeters. So you often actually do measure the volume of solids in milliliters. But they're the same as cubic centimeters anyway. For gases, the more common unit for density would be grams per liter. We use a larger volume for gases usually because gases are not very dense at all. If you measured the volume of a typical gas at typical atmospheric pressure and typical room temperature, you would probably end up with a number that's something like 0.002 grams per milliliter. And that is a small inconvenient number to deal with. It's a much more convenient number if you use a larger volume, in which case you get a density that's more like maybe 2 grams per liter. So that's why we use those units. But then, of course, we could always change those units to kilograms per cubic meter if we have to. Some examples of questions with density. Is, for instance, say you've got a ring with a mass of 4.53 grams and a volume of 0.212 cubic centimeters. And the question is it platinum? Well, what you can do is find the density of this ring and compare it to the density of platinum. You've got the mass, 4.53 grams. We've got the volume in cubic centimeters. And that's the customary unit for solids. So you should be fine just finding the density this way. The density comes out to be 21.4 grams per cubic centimeter. And then what you would want to do is go and look up the density of platinum. The density of platinum is, what do you know, 21.4 grams per cubic centimeter. And so from this information, you can tell that the substance that the ring is made of has exactly the same density as platinum, so it probably is platinum. Or at least you can't say that it isn't. It's possible that the ring could be an alloy of a couple of different metals and the density just happens to work out to be the same as the density of platinum. That seems pretty unlikely. It's probably platinum. Okay. Another example might be suppose you've got an oddly shaped figurine that's made of copper. I say it's irregularly shaped, just meaning that you can't measure the volume by taking measurements with a ruler. and it has a mass of 159.7 grams. And so what is its volume? And so the first thing you'd want to do is look up the density of copper. And this is assuming that the statue or figurine is pure copper. It's in practice probably an alloy with something else, but let's pretend that it's pure copper. And the density of pure copper is 8.96 grams per cubic centimeter. We know from our triangle, oops, yeah. Okay, the density is mass over volume. Well, we've actually got the density, and what we're looking for is the volume. Remember, volume is mass over density. Okay, so 159.7 grams over the density is 8.96 grams per cubic centimeter. Mathematically, to look at what's happening with the units here, you might want to rewrite this as 159.7 grams times 1 over the density. So if the density is 89.6 grams per cubic centimeter, 1 over the density would be the fact that there's 1 cubic centimeter for every 8.96 grams. So you can do this because dividing by something is the same as multiplying by 1 over that thing. We can also do this. And doing it this way makes it clear that grams cancel as a unit, and you end up with cubic centimeters, which is a volume unit. And the answer would be 17.82 cubic centimeters. So now you know its volume. Oh, okay, so I only had 2 examples. All right. As I mentioned in passing above, density changes with temperature. And that's because objects tend to expand with heat. Yeah, I know, I'm really impressed too. So objects tend to expand with heat. In other words, the volume increases as objects get hotter. Well, notice density is mass over volume, and that means as an object heats up, the measurement on the bottom of the fraction is getting bigger as an object heats up, which means the result of that fraction will be getting smaller. So if temperature goes up, density goes down. They're not inversely proportional, but they are related to each other. With solids, the temperature would have to go up a lot in order for the density to go down significantly. For liquids, you wouldn't need quite as big a change in the temperature for a noticeable change in the density. And for gases, though, even a small change in temperature can mean a big change in the density. And so that's especially true for gases. Density can also change with pressure. And that's because if pressure increases, volume tends to decrease. That's especially true for gases, also true to some extent for liquids, but not as much as with gases. So again, volume is decreasing, but for the density equation, the volume is on the bottom of the fraction. So if the number on the bottom of the fraction is getting smaller, you're dividing by a smaller number, which means the result gets bigger. So if the pressure goes up, density goes up. Pressure and temperature have no effect on mass because mass is a measurement of the amount of matter in an object, and temperature is not going to change that, but it can change the volume. And same with pressure. Pressure can have an effect on the volume. And because of that, they can have an effect on the density. Okay, the next subject we need to cover is scientific notation. There's a little bit on this in the main body of the text, but most of it, most of the review is in the appendix, so you can reference that also. Scientific notation is a pretty big and important subject too, and I see by the clock that we're coming close to the end of this segment of the video. We have one more segment to go in this lecture, so I will pick up with scientific notation in a moment. I'll see you then.